Hello everyone, I am Parag. Welcome to CS784 Image Synthesis. This is a new course that deals with how images are created on a computer. Have you ever wondered how an image like this has been rendered, or how a computer can generate images that look photorealistic? So what is rendering? In rendering, we create a discrete view of a continuous world, that is, break it up into pixels. If you zoom into any image that is stored on a computer, you will find that at its finest level it is made up of small blocks, and rendering is just the process of figuring out colors to these blocks or pixels. One of the most common methods of doing rendering is ray tracing or path tracing. If we try and model how illumination moves around in the real world, there is a light source and there is lots of geometry of objects, and the light from these sources bounces off the geometry and reaches a sensor, and the light rays that reach the sensor are captured on these pixels. However, a lot of these rays do not actually reach the sensor. So if we are trying to mimic this process in this direction, it will lead to a lot of wasteful computation. So on a computer, we flip this process. Instead of shooting rays of light from the light source as happens in reality, we instead shoot rays from the camera center or the eye, and then they bounce off from the geometry, and we query the light source to figure out what color is visible at the point where the ray had hit the geometry of the scene. This depends upon the surface properties and how light interacts with the surface. Each ray shot from the eye can contribute to a different pixel in the image. This is known as direct or local illumination. But rays that have been shot can not only bounce back to the light source, they can also bounce around to other points of the scene and then get to the light source. We can accumulate the contribution from multiple such bounces to assign the color to a particular pixel on an image. This is known as indirect illumination, and when both direct and indirect illumination are computed by a rendering algorithm, it is solving for what is known as global illumination. We will learn how to compute global illumination at surface points in our virtual worlds, and the theory and the practical aspects of how we can use these computations to create very realistic looking images. Then we will move on to image-based rendering. The previous method we saw had explicit geometry that was being rendered under a particular illumination, but sometimes you can just capture all the light rays that are bouncing off real world objects in images and use this collection of images to create a representation of the scene without defining any explicit geometry. This is precisely what light field rendering does. There are also images that capture, in addition to RGB color, the depth of the point on the surfaces in the world from the camera center. These are known as RGBD images, and these can also be used to create very large and accurate reconstructions of the world around us. So these methods, which rely purely on images without an explicit geometric formulation in the background, form the crux of what are known as image-based rendering techniques. After learning about image-based rendering, we will move to the hot new area of neural rendering, where we will learn about things like neural radiance fields, where a neural network is actually being used to learn a light field around an object, and then it can be queried to generate novel views of these objects. And absolutely fresh out of the conference pipeline from SIGGRAPH this year is Gaussian splatting, which is another way of capturing the appearance of objects from images, and has the advantage of being much faster in comparison to NURFs, which are neural radiance fields, and producing very photorealistic results for novel view synthesis. We will look at the problem of inverse rendering, which is when we are given real photographs, can we figure out what was the illumination around points in that photograph that existed in that environment when the photograph was taken. Which will bring us to another very interesting topic, which is known as differentiable rendering. So we have looked at forward rendering, which was global illumination. We have looked at image-based rendering, and then we have looked at inverse rendering. How about that you make a guess about the scene geometry, render it using your path tracer that we talked about in the global illumination context, compare it with an expected photograph of that scene, and then whatever loss you get, you use that to guide a gradient descent algorithm to make better searches about the scene parameters that you are trying to ascertain, like the geometry or the material properties or the color or the light position, the directions, you name it, and differential rendering can solve it. Then we will move on to specific rendering methods that enable high fidelity virtual and augmented reality. Here we will look at foveated rendering, where we actually render only a part of the image that we are focusing on, and we predict the rest of the image with lower fidelity using a neural network. We also look at issues which try to solve the vergence accommodation conflict, which causes discomfort when using VR headsets for very long periods of time. And while going through all these exciting methods of image synthesis, we will actually look at the nitty-gritties and the nuts and bolts of image synthesis. We will talk about color spaces, high dynamic range imaging, spherical harmonics, BRDFs. We will try and figure out methods of solving the rendering equation. We will talk about relighting of scenes which have already been lit, and we will talk about intrinsic image decompositions. All these terms might make no sense to you right now, but they are essential bits and pieces of the jigsaw of image synthesis. And then of course there is the very exciting neural question. Great strides have been made into image synthesis by latent diffusion models. As we can see that given just one image, you can now guide a diffusion model to churn out a host of outputs, which can take semantic cues, it can take pose cues, it can take color cues, depth cues, a whole lot of input from that single image, and create a plethora of synthesized images. We will also look at deepfakes, which have both ethical and non-ethical uses. We will try to figure out whether there are good methods of detecting fake images and figuring out biases in data that has been used to train models for image synthesis. And of course there is a question of who owns this data, and once you have trained a model on this data, then who owns that model? The course is going to involve a lot of hands-on exercises which will need you to program in C++ and Python. And we will also look at some digital content creation platforms like Blender, and we will try and do some assignments in Blender to aid our understanding of various concepts in the course. For all this and more, sign up to CS784, and I hope to see you in the first lecture for the course. Thank you.